Hi everyone! In one of our previous courses, we introduced the Public Network IPv4 over SRv6 BE scenario. In the early stage of SRv6 development, thanks to the reachability of IPv6 routes, SRv6 BE is advantageous in fast service provisioning. However, as networks evolve rapidly, the best effort mode of SRv6 BE cannot meet differentiated service requirements. In contrast, SRv6 TE Policy can implement traffic engineering and work with a controller to better meet differentiated service requirements. As such, in this course, we'll show how to configure Public Network IPv4 over SRv6 TE Policy, introduce packet exchanges, describe the usage scenarios of key commands, demonstrate the detailed configuration verification process, and summarize route advertisement and packet forwarding processes in the last part. Now let's look at the networking solution. Let's take a network with 5 devices as an example. PE1, the P, and PE2 all belong to AS100. A bidirectional SRv6 TE policy needs to be deployed between P1 and P2 to carry public network IPv4 services. The configuration roadmap for this scenario is as follows. First, enable is on P1, the P, and P2 to achieve basic route reachability. Second, configure an SRv6 TE policy between P1 and P2. Third, configure a BGP IPv4 unicast peer relationship between P1 and P2 to advertise routes between R1 and R2. Let's start by looking at how to configure is. Is configuration helps achieve basic route reachability. This is because SRv6 is implemented through is extensions. These devices require similar is configurations, which mainly include global and interface-specific configurations. Next, let's see how to perform basic SRv6 configuration. Involved operations are as follows. First, enable SRv6 globally. Then, configure a source address for SRv6 encapsulation. After that, create a locator and configure an end.xseed in the locator view to represent the adjacency from P1 to the P. After completing the configurations, we need to enable SRv6 in is and configure the device to advertise the corresponding locator route. After completing the preceding configurations, we can check the is routing tables on the PEs and P. The command outputs show that the is routing tables contain both subnet and locator routes. In addition, we can see that P1 has learned the locator routes of P2 and the P, and that the P has also learned such locator routes. Moving on, let's look at SRv6 TE policy configuration, which mainly involves the following steps. The first step is to run the segment list command to create an explicit path from P1 to P2 and specify each hop. In this example, this address indicates the first hop and .xseed, representing the adjacency from P1 to the P, and this address indicates the second hop and .xseed, representing the adjacency from the P to P2. The next step is to create an SRv6 TE policy whose endpoint is a loopback interface address on P2, and color value is 101. We also need to specify a candidate path in the SRv6 TE policy and configure the path to reference the previously configured segment list. Finally, let's see how to configure BGP. We should first configure an eBGP peer relationship in the BGP IPv4 unicast address family for route advertisement between P1 and R1, as well as between P2 and R2. This example uses eBGP. We can also use another routing protocol. Then we need to run the opcode and DT4 command to configure an SRv6 and .DT4 seed. This operation is optional, because using an end.dt4 seed dynamically allocated by BGP is also allowed. After an end.dt4 seed is configured, it is added to the local seed table. In the local seed tables on P1 and P2, we can see that each end.dt4 seed is bound to a public network instance. An end.dt4 seed consists of a locator and an opcode. The locator directs packets to a specified PE in the SRv6 domain, and the opcode is used to associate the PE with the corresponding public network instance. Next, let's see how to establish a BGP IPv4 unicast peer relationship between the PEs. This requires several key steps to be performed in the BGP IPv4 unicast address family view. The first step is to add the seed attribute to the BGP IPv4 routes to be advertised. If no manually configured seed is available, a dynamically allocated one can be used. The second step is to enable route recursion to SRv6 TE policies. The third step is to enable the current device to exchange routes with the BGP IPv4 unicast peer with a specified IPv6 address. The fourth step is to enable the current device to exchange prefix seeds carried by public network IPv4 routes with the specified IPv6 peer. Following that, we need to configure route coloring on the PEs. The main steps are as follows. First, define a route policy and specify the color attribute 0101. The value 0, which is fixed, indicates the color flag. The color value is 101. A route can recur to an SRv6 TE policy only if the color value of the route is the same as that of the SRv6 TE policy. Second, apply the route policy to routes to be advertised to the specified BGP peer, and enable the current device to advertise extended community attributes. This step can be skipped if the route policy is applied to routes to be received. Finally, configure and apply a tunnel policy on the PEs to import public network IPv4 traffic. The configuration mainly includes the following steps. First, create a tunnel policy and specify the tunnel type to be selected and the number of tunnels that can participate in load balancing. Second, create a tunnel selector and select a tunnel policy for the involved routes. Third, enable public network route recursion to SRv6 TE policies in the BGP IPv4 unicast address family view. After a BGP IPv4 unicast peer relationship is established, the PEs exchange update messages. Next, let's look at the BGP update message format. We can see that the update message carries multiple path attributes, including extended community attributes that contain the color attribute, the end.dt4 seed, which is configured on PE2, is carried in the prefix seed attribute. As for an LRI, the address family identifier is IPv4, and the subsequent address family identifier is unicast. The next hop of the route is the loopback interface address of PE2. The route prefix is the route prefix sent from R2. Now let's have a look at the BGP IPv4 routing table on P1. We can see that the next hop of the route sent from R2 is the loopback interface address of P2. The detailed route information shows the color attribute and the prefix seed carried by the route. We can also see that SRv6 TE policy is displayed as the outbound interface for route recursion. The preferred BGP route enters the IP routing table. As such, we can also see the route of R2 in the IP routing table. According to the displayed information, the route has successfully recursed to an SRv6 TE policy. The BGP route on P1 will be sent to R1 through the peer relationship. As such, we can see this route in the BGP routing table of R1. The preferred BGP route on R1 enters the IP routing table. As such, the IP routing table on R1 contains this route. If we ping R2 from R1, we can find that the ping is successful. This indicates that the configuration is successful. That's all about the implementation of Public Network IPv4 over SRv6 TE policy in the control plane. Next, let's look at the packet forwarding process. Let's ping R2 from R1 to simulate packet encapsulation and check the SRv6 TE policy-based data encapsulation format. We can see that ICMP encapsulation and then IPv4 encapsulation are performed for the request packet sent from R1. After receiving the packet, P1 performs SRv6 encapsulation, encapsulating the packet with an SRH in which the last seed is the end.dt4 seed of the public network instance configured on the peer PE. In contrast, the reply packet is transmitted over an SRv6 BE path without carrying any SRH. Finally, let's summarize the route advertisement and data forwarding processes. Taking route advertisement from R1 to R2 as an example, the advertisement process mainly consists of 3 steps. First, IPv4 route advertisement from R1 to P1 through the eBGP peer relationship. Second, public network IPv4 route advertisement from P1 to P2 through the BGP IPv4 unicast peer relationship. Third, IPv4 route advertisement from P2 to R2 through the eBGP peer relationship. After that, let's look at the data forwarding process. Taking data forwarding from R1 to R2 as an example, the forwarding process mainly consists of the following steps. First, the original IPv4 packet is sent to P1 through a specified interface. Second, P1 searches the public network IPv4 routing table according to the IPv4 destination address in the packet and finds the associated end.dt4 seed. Then P1 encapsulates an SRH and the end.dt4 seed into the packet. In the forwarding phase, according to the instruction bound to the end.x seed, P1 decrements the SL value by 1, changes the destination address to this address, and then forwards the packet through the outbound interface bound to the end.x seed. The P searches the local seed table according to the outer destination address and finds a matching end.x seed. According to the instruction bound to the end.x seed, the P decrements the SL value by 1, changes the destination address to this one, and then forwards the packet through the outbound interface bound to the end.x seed. Fourth, P2 searches the local seed table according to the outer destination address and finds a matching end.dt4 seed. Then P2 removes the IPv6 header, finds a public network instance matching the end.dt4 seed, and searches the public network IPv4 routing table for packet forwarding. That's all for this course on Public Network IPv4 over SRv6 TE policy. Thank you for watching.